All right, let's stop at 40 seconds. It's 5 more seconds, Joe.
I assume he's doing this.
Ice fishing? What are y'all talking about? Sorry, I'm still thinking about orientation. A is right. You aim directly at the image because your laser gun will go straight and then it's going to bend just like the ray from the fish. It'll refract just like the ray from the fish. Come back to this. Look, I brought a big piece of glass. You can see the light actually bends. Turn the lights off. Okay. Not sure if y'all be able to see this in the back, but this is just a big piece of acrylic, and I can run my laser through here, and if I move it like this, see how it bends? I'm moving actually at a fairly steep angle, but then it moves away from or bends towards the normal as it goes into the glass. Can y'all see it up front here? Can y'all see that here? It's doing a little bit of both, and we'll talk about that later. You get refraction inside of the glass when it moves from the air to the glass, or the glass, and then you also get reflection. We'll talk about that. That's what's going on. All right. When I was a kid, I went to the boarding school, like past science school, and we had early cannabis in Mississippi. And so we would sit up in our dorms, and we would point this down at the ground. We were on the Mississippi University for Women campus in Columbus, and there were men there too. But the college students would like chase them around like little cats. Everybody just like, what's going on? All right, you see refraction in various things. You can see a straw in a glass. It looks like it bends, or a pencil. You might have put a pencil into a glass of water, and when you do that, if you have a pencil, it looks like the pencil sort of breaks in between the interface, and that's because light bends as it goes through. You can also make things disappear. I have a video I want to show you. Similar question what we had before. I realize my inequalities are not written correctly. I'll fix that for the exam. All right, well, let's stop at 120. 120. 5 more seconds. All right, so similar to what we've done before, I think about how does my light bend. Here it's going to speed up as it goes through. So that tells me that N2 is less than N1. So if N2 is less than N1, that gets rid of that one, and it gets rid of that one, because N2 has to be less than N1. And then as it moves from N2 to N3, it moves in this direction. That means it slows down right there. So N3 is bigger than N2. Now both of these have N3 bigger than N2. So I need to think about now, how is N3 related to N1? So I can redraw this. I would have N1, N3. It's like I just sort of bump out that second medium, but the light will still move from N1 to N3 in the same way. And as I said, we'll show that mathematically later, but just for now, just nod your heads and agree. But my wavefront comes there. Is it going to speed up or slow down when it goes to this? It's going to slow down. That tells me that N3 is bigger than N1, so that gets rid of C. So this is the right answer, A. And you have to look at each individual interface as well as the interfaces of the two outer media. See, before we go on, I wanted to show y'all something because we're going to skip ahead to the electromagnetic spectrum, but then we'll come back to this quick test, these other two, because we might not have time to finish this, but I brought my infrared camera, so I wanted to go ahead and skip ahead, but we will go back to those other two things, okay, because we are responsible for that as well. So the electromagnetic spectrum, as you know, you should have learned this in, I don't know, 6th grade or whatever, maybe earlier. But light includes all different types of radiation. They have a different wavelength and frequency, and they're related by the speed of light. And so this is the wavelength times the frequency. Sometimes for frequency we'll use the Greek letter nu. It sort of looks like a stripped V. Wavelength has SI units of meters. Frequency has SI units of hertz. And this is equivalent to 1 hertz is equivalent to 1 inverse second. So a frequency is 1 over time. We're going to have a chapter on sound, and we'll talk more about wavelength and frequency then. But the spectrum, I want you to know the different parts of the spectrum, and then I also want you to know how if you have the wavelength or the frequency, that you can calculate one or the other, because it's dependent upon the speed of light. So say, for example, our wavelength was 2 meters. It's like a radio wave. Then the speed of light is 3 times 10 to the 8th meters per second. The wavelength is 2 meters, and so then I can calculate my frequency. So the frequency of this particular wave would be 1.5 times 10 to the 8th hertz, or 15 gigahertz, or gigahertz. So be able to calculate for the wavelength or the frequency. You have some in your homework. We'll do some problems later. But be able to, given the wavelength, be able to calculate the frequency. Given the frequency, be able to calculate the wavelength. You also need to know the different parts of the spectrum. The spectrum goes from radio waves all the way up to gamma rays. And you need to know those in order of energy, in order of frequency, and in order of wavelength. So down on this end, it's long wavelength, so big wavelength, but small frequency. On this end, we have very short wavelength. That's a very small wavelength, but a very high frequency. And then if we think about energy, we have small amount of energy. On this end, radio waves carry very little energy, but gamma rays, and this is why they're so damaging to us, have a very large energy, or very big energy. In fact, it turns out that the energy is proportional to the frequency. The higher the frequency of the radiation, then the more energy it's going to carry. So gamma rays, X-rays, UV rays, they're all going to have more energy than the things from the long wavelength end of the spectrum. You need to know radio waves, microwaves, infrared, optical, UV, X-rays and gamma rays in particular. Don't worry about FM radio and radar. But they fall down there with radio waves. They're just sort of an extension of radio waves. All right, and then also in the visible spectrum, we just see a tiny little sliver of this electromagnetic spectrum. We have the colors of the visible spectrum, and you all know that it's the Roy G. Biv. Where I have my red, orange, yellow, green, blue, and then my indigo or violet down at the end. Violet's really strong. All right, I brought an infrared camera today. This has, in just a second, let me hook it up. My remote fall down over there, y'all? My Apple TV remote? You see it over there? Okay, guys, I'm sorry. Give me just a moment. I'll find my remote. Well, maybe I can. All right, what do y'all want to watch? Sing, or Patriots Day, or Mona? Moana? How do you say that? All right, guys, here we go. All right, so this is an infrared camera. Contractors use this often to look for hot spots. Like if you look at those windows over there, they look there. Oops, there's a bunch of people over there. But the windows, that's I'm sorry, guys. All right, guys, we'll just call it a day. If I get it to work, I'll bring it back next time. Wait, no, hold on just a second. I have a couple more minutes. Hey, guys, hold on just a second. Let's see, I think it's working now. It's just our internet is a little slow. No, it's not working. Y'all can go. I'm sorry. I'll get it working next time.